Hi all, in the last class we have discussed this theorem, theorem 1. If S is equal to set of all V1, V2, etc. Vn is a basis for a vector space V, then any set containing more than n vectors is linearly independent. That means if a basis contains a certain number of elements, then we can never expect a linearly independent set with more than number of elements of that set. That means any set with more than number of elements more than this set, then that set will be linearly dependent. Okay, this is what we have discussed in the last class. Then we can easily follow this corollary. S is equal to V1, V2, etc. Vn is a basis for a vector space V. Then every linearly independent set, okay, of vectors in V must contain n or fewer vectors. Okay, that means if you choose a set S with this much elements V1, V2, etc. Vn, this is the basis, is a basis. Then if you choose any set S prime, okay, S prime S prime is linearly independent set. That means it contains elements beta 1, beta 2, etc. Beta m is linearly independent, then we can say that this set has m elements which is less than or equal to n. This is what this corollary says. Okay, we know that is because we have in theorem 1, if this is the case, if m is greater than n, implies the set S prime is linearly dependent. This is what we have proved in first theorem. So this is nothing but the contrapositive of that. If m is greater than n, S prime is linearly dependent. The contrapositive is S prime is not linearly dependent, that means linearly independent, then this never happens. The negation of this happens, that is m is always less than or equal to n. That is what we have seen in this corollary 1. Now we have theorem 2. Every basis for a finite dimensional vector space must contain the same number of vectors. That means if we have two different bases S and T, then we can say that this basis means this is linearly independent and spans V anyway. Okay, so this is we use the idea of linearly independent independency of these vectors. First of all, you take this as a basis, and any linearly using the previous corollary, we can say that any linearly independent set contains contains elements fewer than this set. Okay, so first you take this as a basis, and this is linearly independent set. So we can say that P is always less than or equal to n. Okay, now you think about the other way around. This is a basis and this is a linearly independent set. So since this is a basis, then every linearly independent set contains fewer elements than this. So that is, if this is the basis, then we can say that n is, since n is linearly independent, then n is always less than or equal to P. So these two statements together imply that n is equal to P. Okay, so this is the proof of theorem 2. Every basis of any two bases of the vector space, finite dimensional vector space, contain equal number of elements. Now we have some example. These are some simple examples, so you go through it. Example 6 and all. This is example 7. In example 7, we can choose a basis of M22. That means set of all 2 by 2 matrices. So this is one of the basis of this M22. Because these are all linearly independent, you can easily prove that these are linearly independent by choosing C1 times this plus C2 times this equal to plus this C3 times this plus C4 times this is equal to 0. 0 means 0 matrix. Then you can easily get C1, C2 and C3, C4 are all 0. So this is the basis, and we can see that any A, B, C, D, the matrix A, B, C, D can be expressed as a linear combination of this. So the dimension of M22 is 4. So you write. You go through all this example 6, 7, 8. Now we have theorem 3. So this is exactly same as theorem 1. In an n-dimensional vector space, so this is a particular case for that. In an n-dimensional vector space, every set of n plus 1 or more vectors is linearly independent. because we can say that if a vector space is n dimensional, then basis contains exactly n elements. Every basis containing exactly n elements. So every linearly independent set contains the fewer elements than that. Okay, and theorem 1 says that if any set containing more than that elements is always linearly dependent. So this is equivalent to theorem 1. And now we have theorem 4. Theorem 4 says that for a subspace of a particular vector space, or that is a R3 is a vector space of dimension 3, then this theorem states the possibilities of the dimensions of the subspaces. If U is a subspace, then dimension of U is equal to 0 is possible. Then U contains only the additive identity 0 0. Then only the dimension will be 0. Okay, so that is trivial thing. And if dimension of U is equal to 1, then we will prove that the graph of U is a straight line through the origin. Graph means set of all the sketch of set of all points in U. Okay, we will prove that this dimension of U is equal to 1, then that is nothing but a straight line passing through origin. Okay, and if dimension of dimension of U is equal to 2, then we will prove that the graph of U is a plane that includes the origin. To prove the second case, we assume dimension of U is equal to 1. In this case, we can get a basis vector for this subspace U, and every vector V can be expressed as some C times U. Okay, so this is the case if dimension of U is equal to 1, and we can say that the sketch of this or the graph of this is a straight line, because if you consider an arbitrary element x, y, z this is our V, and U is a fixed element, U is equal to x naught, y naught, z naught, then this equation says that we can write x, y, z is equal to C times x naught, y naught, z naught. This is an equation of the straight line. Okay, x, y, z belongs to a straight line. That is x by, from this you can write x equal to C x naught. That is x by x naught equal to C. That is equal to x minus 0 by x naught equal to C. Okay, so that is equal to, similarly, y by y naught, y minus 0 by y naught is also C. That is equal to z minus z naught, z minus 0 by z naught. So from this you can say that this is a straight line passing through this x naught, y naught, z naught is a fixed numbers. Then this is this x, y, z lies on a straight line passing through 0 0 0, which shows that the graph of U is the straight line. For the third case, for 3, we assume dimension of U is equal to 2. In this case, we can get two linearly independent vectors V and this V1 and V2. This is V1 and V2. Then since this is linearly independent, then you can get this is our V1 and this is our V2, and you consider all the linear combination of this. This is U contains all the vectors of the form alpha V1 plus beta V2. So this will give the entire plane containing this V1 V2. Okay, but by putting alpha and beta is equal to 0, you can get 0 0 is a vector in this U. So you can get set of all vectors as a linear combination of that lie in this plane, which passes through this 0 0. Okay, because the 0 0 is also an element of this U, because if you properly choosing this alpha and beta, you can say that this is a 0 0 is a point on this plane. So this proves theorem 4. Now we have theorem 5. Let V1, V2, Vn be a basis of a vector space V, and let V is an arbitrary element of V. If we suppose we have two different expression in as a linear combination of elements of this basis vector V1, V2, etc. Vn, and we'll prove that these two expressions are the same. Okay, that means if once you fix a basis vector V1, V2, Vn, then this V can be uniquely expressed as a linear combination of elements of this V1, V2, etc. Vn. That is what to prove. So suppose V has two different expressions as a linear combination of this v1 v2 vn. Say v is equal to c1 times c1 times v1 plus etc cn times vn. Similarly, v is equal to d1 times v1 plus etc dn times vn. But since these two quantities are the same, then difference will be 0. Then you can get v minus v, that is equal to this minus this one, that is equal to, by subtracting the corresponding elements, c1 minus d1 times v1 plus c2 times v2 minus d2. This is c2 minus d2 times v2, this is not there, and plus etc cn minus dn times vn. If this is the case, this is a linear combination of v1 v2 etc vn as 0. Now use the linearly independence of this v1 v2 vn. Whenever a linear combination of v1 v2 vn is 0, then all the coefficients should be this the zero scalar. So this c1 minus d1 will be 0, c2 minus d2 will be 0, etc. cn minus dn will be 0. Okay, so this is nothing but the definition of linearly independent vectors. Whenever x1 v1 plus etc xn vn equal to 0 implies each xi equal to 0. So that is what we have applied here. Then you can get c1 equal to c2, c1 equal to d1, c2 is equal to d2, etc. cn is equal to dn. Then we can say that these two expressions are the same. Now we prove theorem 6. Theorem 6 says that if S is a spanning set, that means we have a subset of V such that span of S, set of a linear combination of S is nothing but V. Okay, then we can say that there exists, or S contains some element, S contains a subset which is linearly independent and spans V. That means S contains a basis. Okay, or you can reduce this elements of S to get a basis vector, basis of V. Okay, that is the first statement. And second statement says that whenever we have a linearly independent set alpha 1 etc alpha k, then this can be extended to a basis of V, or this is a part of a basis of V. Okay, so the idea of the proof of these two statements are the same. If we take S as the first case, say alpha 1 etc alpha n or alpha m is a spanning set, is a spanning set of V. Assume that dimension of V is equal to n. Suppose you have this set. Okay, if this spans V, we can say that for this when you take alpha 1, then alpha 1 belongs to V, implies alpha 1 is a span of this. Alpha 1 can be written as a span of, or any alpha I can be written, any alpha I belongs to V, we can that alpha is a span of alpha 1 etc alpha m. Okay, so first you if this is linearly independent, then we are done, because this spans V, and if this is linearly independent, then we can get this as a basis, and m will coincide with n. Okay, if this is not linearly independent, you can say that one of them can be expressed as a linear combination of others. Okay, so if this is not linearly independent, we can collect an alpha k that can be expressed as the first of all, you can write this alpha c1 alpha 1 plus etc cm alpha m equal to 0 with not all ci equal to ci is 0. Okay, so this is the definition of linearly dependent vectors. If this is not linearly independent, then you can collect a non-zero coefficient such that this combination is 0. Okay, so choose one such coefficient, say name it as some ci or c k. Then you write if ck is not equal to 0, then choose the first such one. Okay, so that is first such or last such ck not equal to 0. Then you can write the ck alpha k can be written as minus c1 alpha 1 minus c2 alpha 2 etc minus c k minus 1 alpha k minus 1 plus etc. This c. So I choose the last one, the largest suffix. That means after that all the coefficients are 0. So if this is the case, we can write this is equal to this one, and alpha k can be expressed as minus c1 by ck alpha 1 minus c2 by ck alpha 2 and all. Okay, this shows that this alpha k is a linear combination of alpha 1 alpha 2 etc alpha k minus 1. Okay, so which shows that you can remove alpha k from this set. Okay, that means the span of this set is same as span of alpha 1 etc alpha k minus 1 alpha k plus 1 etc alpha n. Okay, you can remove that one because this alpha k is a linear combination of the others. This shows that you can reduce this set to the span without changing the span. You can reduce the set to another set that contains exactly m minus 1 numbers. Okay, again this is a vector space. If this is linearly independent, then the spans and linearly independent, and that will give V. That means this is a basis. Okay, so if this is not linearly independent, then apply the same thing and reduce one more. Okay, so this continuing this process, you can get a basis vector, the basis consisting of the vectors from this set. Okay, this shows that every spanning set can be reduced to a basis. Okay, using the similar argument, you can prove that every linearly independent set can be extended to a basis. Okay, we know that if you have a linearly independent set, say S prime consisting of vectors alpha 1 etc alpha k is linearly independent, we can say that then k is always less than or equal to m. We already discussed that every linearly independent set contains exactly the fewer elements than the basis element. Okay, so if this is if dimension of V is n, then that k is always less than or equal to n. Okay, now since this is linearly independent, then consider the span of this one, span of alpha 1 etc alpha k. If this is equal to V, then we are done. If this is equal to V, that means this is a basis. Okay, it is linearly independent, and if it spans V, then that is the basis. Okay, otherwise if the span is not equal to V, then choose a beta does not belong to the span of or we can write beta belongs to V minus span of alpha 1 etc alpha k. We know that these two are not equal. Okay, so we can collect this one. Then the set alpha 1 etc alpha k by adjoining this beta to the set is linearly independent. Okay, why it is linearly independent? If we choose c1 alpha 1 plus c2 alpha 2 plus etc ck alpha k plus some d beta equal to 0, we can easily prove that all these coefficients are 0. First of all, you write this, suppose this d. Okay, if this d is not equal to 0, if d not equal to 0, the consequence is this beta can be written as a linear combination of minus c1 by d times alpha 1 plus etc. That means beta can be expressed as a linear combination of alpha 1 alpha 2 alpha k. So beta would be an element of span of alpha 1 alpha 2 alpha k. So that is a contradiction because beta is selected from V minus this set. So we can never expect this d is non-zero. Okay, that means d equal to 0. Whenever d equal to 0, the other things, the c1 alpha 1 plus etc ck alpha k should be 0. Consequently ci's are 0 because this alpha 1 alpha 2 alpha k are linearly independent. Okay, so when you adjoin a vector beta from the outside of the span of alpha 1 alpha 2 alpha k, in case this is not equal to V, then this set, the set obtained by adjoining beta to this linearly independent set, is again linearly independent. If this spans V, then we are done. This is a basis. Otherwise, you can again extend this set to the by adjoining some beta 2 from outside the span of this. So extending this, you can get a basis for B. So this proves the second statement. Every linearly independent set can be extended to a basis of V.